Hello Chem 111, and today we are going to be doing the gas laws of chemistry. The gas laws are just a way in chemistry to relate pressure, volume, temperature, and amount in regards to a gas. And these four properties are actually related to one another, though that wasn't always known. One of the first gas laws is Boyle's law. Now, Boyle's law is valid whenever a certain amount of gas, grams, moles, whatever, is held at constant temperature. When it is held at constant temperature, the following is observed. Pressure and volume are inversely proportional to one another. Essentially, as one increases, the other has to decrease, such that the product of pressure and volume for a gas will always equal some value. Now, basically that means that if under one set of pressure and volumes equals some value, well then under a different pressure and a different volume, you would still end up getting the same value if you multiplied pressure and volume. Therefore, Boyle's law basically states that one set of pressure and volume measurements will give the same value as a different set of pressure and volume measurements for a gas. This is true because, say, if you increase pressure, then volume has to decrease. Or if you increase volume, then pressure has to decrease accordingly, such that you end up getting the same product. Now, another law would be Charles' law. Charles' law is valid when you have a certain amount of a gas that is held at constant pressure. And what is observed that when the gas is held at constant pressure, volume and temperature are proportional, such that if you were to take under one set of conditions a gas's volume and divide it by its temperature, it will end up giving the same value as its volume divided by temperature if those values were different under a different set of conditions. So Charles' law is simply volume divided by temperature will always equal the same value, or V1 over T1 will always equal V2 over T2. A similar law to Charles' law would be Gay-Lussac's law. This is essentially valid when a certain amount of gas is held at constant volume, such that pressure divided by temperature of a gas always equals some constant value. Therefore, Gay-Lussac's law is simply pressure divided by temperature in one scenario will equal pressure divided by temperature in another scenario, or P1 over T1 equals P2 over T2. Now, as these laws were essentially observed, it was eventually determined that you could combine those different laws together to form the combined gas law. This is essentially a way of relating pressure, volume, and temperature as long as the amount of gas is kept the same. Therefore, essentially, the product of pressure and volume, then divided by temperature, will always equal the same number. Therefore, the pressure, volume, and temperature in one scenario for a gas will equal the product of pressure and volume divided by temperature in another scenario for that gas. Or in other words, P1 V1 divided by T1 equals P2 times V2 over T2. Another gas law would be Avogadro's law. Now this is slightly different than the other ones we talked about. This one actually covers the amount of gas, and it is essentially valid if a gas is held at constant pressure and temperature, such that if volume and the amount of gas are the only two factors that are changing, then the following is observed, as basically volume and the amount are proportional to one another. Basically, if you increase the volume that you store gas in, you can fit more into it. Pretty straightforward. Now, Avogadro's law basically states that volume divided by the amount in moles for a gas will always equal the same value. Therefore, in one scenario, volume divided by amounts will equal, in another scenario, its volume divided by its amount of gas. Or V1 divided by N1 equals V2 divided by N2. Now, where this is all important is that as scientists were discovering that pressure, volume, temperature, and the amount of gas were all related, they eventually discovered that there was some hidden constant that was universal among all gases. And that is called the universal gas constant. Essentially, it is represented by capital R. Now, depending on the units you use for pressure, volume, amount, and temperature, you can get a range of different values for R. Now, most of these are not relevant for, per se, chemistry. Some might make more sense if you're an engineer, or if for whatever reason you're working in PSI, cubic feet, cubic meters, or even grams instead of moles. For chemistry, it is actually the top left two that actually matter, where 8.314 joules per mole Kelvin, that's relevant in thermodynamics and electrochemistry. For gas chemistry, it is the second from the top, 0.082057 or 0.08206 liters atmospheres per mole Kelvin. That value is what we use in place of R for our universal gas constant, because for pressure, volume, and amount of temperature, we're usually looking at atmospheres, liters, kelvins, and moles. Now, the importance of understanding the universal gas constant is that you can form the ideal gas law. This is a way of essentially representing a gas's pressure, volume, amount, and temperature, such that you only need to have one scenario as opposed to two different scenarios. And in doing so, if you only know 4 out of 5 of these values, then you can plug all 4 of those values into the ideal gas law to find the unknown, such that if you know pressure and you know the amount and you know temperature and you know the gas constant R, you can determine the volume that gas has. Now, the ideal gas law is essentially PV equals nRT. The product of pressure and volume equals the product of amounts of gas times the temperature times the universal gas constant R. Now, for the ideal gas law to be valid, there are essentially 2 assumptions that are being made. One is that gas particles do not interact with one another. They effectively, according to the ideal gas law, the particles of a gas, they ignore each other. They're not bouncing off each other. They're not attracted or repulsed. This is not true in real life, but it's an assumption that oftentimes gives a good enough answer for what we're working with. Now, the second assumption is that the volume of those gas particles is negligible compared to the volume of the empty container the gas is in. Each particle, each molecule of a gas, it has a tiny volume associated with it that is subtracting from the overall volume of the container the gas is in. However, usually we can ignore the sum of those particle volumes because they are often much lower than the overall volume of the container. Now, the real gas law, the final gas law that we'll essentially cover, also called the van der Waals equation for the real gas law, this essentially describes real gases, or the gases that we interact with on a daily basis. And the real gas law describes real gases by essentially making 2 corrections. One is a correction to the pressure by basically correcting for the molecular interactions or the attractions that are observed between gas molecules. And then another correction is for the correction when it comes to the molecular volume, or the volume of all those gas particles, and what they take away from the volume of the container the gas is in. Essentially, what this real gas law is, it's the product of, or it is the sum of pressure plus A times amount squared over volume squared. And then that multiplied by volume minus the product of amount times B. And all that will equal nRT. Now, A and B, they are essentially correction factors. They are constants for that particular gas. They will differ whether you're talking about water vapor, carbon monoxide, or nitrogen. For any particular gas, it will have its own set of A and B constants. Luckily, those, for the most part, have already been determined through experiments, so there's no real need for any student to determine the values on their own. And usually if you were to have those on exam or a formal test, they would be given to you. Now though, for this class, you don't actually need to use any of the individual gas laws or the real gas law because it's a little more complicated than what the class needs. However, for this class, you should have an understanding of the ideal gas law, PV equals nRT. So an example of working with the ideal gas law would be this problem. A 3-liter container was filled with water vapor until the pressure reached 4 atmospheres. If the gas has a temperature of 200 Kelvin, what is the amount of gas in moles, assuming ideal conditions? So, assuming ideal conditions, that means that we're going to assume that we're using PV equals nRT and not the corrected version or the real gas law. And to solve this, essentially, we just have to recognize that we have volume, pressure, temperature, as well as the universal gas constant. Therefore, the only thing we don't know is the amounts. Therefore, rearranging PV equals nRT to solve for n, we can essentially have pressure times volume divided by the gas constant times temperature. And that will equal our amounts in moles. Plugging in the values that were given in the word problem before would be 4 atmospheres multiplied by 3 liters divided by the product of 0.08206 atmospheres liters per mole Kelvin times 200 Kelvin. And what that would end up being is 12 over 16.412 moles, or 0.73 moles of water vapor. Now then, that's essentially it for gas chemistry for Chem 111. As an extra credit bonus assignment that will be due the end of day this Friday, similar to the previous slide. However, this word problem is an 0.250 moles of hydrogen sulfide gas was filled into a 0.4 liter container. What would be the pressure of this gas at 298 Kelvin? Again, assume ideal conditions. So the formula you'll use is PV equals nRT. You already have the amounts, the volume, and the temperature. Therefore, and you have the universal gas constant 0.08206. Therefore, if you can determine the pressure and submit that, then that'll be good for this week, guys. And, well, that was a nice, beautiful, short lesson on all the main gas laws of chemistry. As always, you are a pleasure to teach, and, well, we have 2 more lessons until we're done with this semester. Go.